welcome. In this video, we are going to explore vectors, mostly in 2-space. I'll talk a little bit about 3-space if I remember, but for the most part, we're just going to be in 2-space. So let's talk about what a vector is. A vector is a directed line segment. So in other words, I have a length to it and I have some sort of direction. The length that we have is called the magnitude, and the direction is however I'm directed. Now, typically, when we talk about the direction, we are usually looking at the angle in reference to the positive x-axis and where that vector is from there. If I have 2 points, such as this, where I have point 1 and point 2, and I'm going to make a vector from point 1 to point 2, then I take my starting position, and to my ending position, I count. How did I get there? Well, this is my change in x, which in this case is 4 minus 2. And this is my change in y, which is my 6 minus 2. So this vector is 3, 4. That tells me that from the beginning to the end, I have gone positive right 3 and I have gone up 4 from the beginning to end. Now, this vector is also a vector, 3, 4. I start at -2, 3, and I end at 1, 7. I still went right 3 and up 4. These two vectors are equivalent because they have the same length and they have the same direction. So when we are talking about a vector, we typically talk about the vector in standard position, which means that we have a vector that starts down here at 0, 0, just like we'd expect. And wherever it ends on the xy plane, the ordered pair of where it ends, we write it as a vector, where it's v1, v2. In the ordered pairs on the xy plane, it would look like this, but as a vector, it would look like this. Now, some books have your vector in bold, so you're going to see it in bold. That is equivalent to this notation. So they are equivalent. It just depends on the book that you are looking at or the homework, however it is designed. We talked about the magnitude and the direction. Now, if we think about the fact that my direction is the angle off of the x-axis, this is not going to be anything surprising than what we haven't already done. The tangent of theta is my b value over my a value. We're familiar with writing this as my tangent of my theta is equal to my y value over my x value. Now remember, this is the x part and this is the y part if they were ordered pairs. So my direction is now in terms of b and a, where b is the y component and a is the x component. And again, the angle is the tangent inverse. And don't forget to draw a sketch so you know if you are actually getting that angle or if you have to add pi to it or some other shenanigation like that. The magnitude is nothing surprising. You'll see the magnitude noted that way, or you may see it noted in this manner. Either way, we're talking about the magnitude, which is r squared, if we are talking about the ordered pairs. So that, again, is nothing new. So all it's doing is like just putting an extra layer on sine, cosine, and tangent. So when we are talking about a vector, we usually talk about it in two forms, which is the magnitude and the direction. If they have the same magnitude and they have the same direction, regardless of where they start out, they are the same vector. We also need to introduce what happens when we have a magnitude of 0. Well, this means we are the 0 vector. So again, we talked about if they're equal, then we just say that they are equal, which means they have the same magnitude and the same direction. Some properties that we get with magnitude and direction, that my magnitude has to be greater than or equal to 0, because remember, it is r squared has to be equal to, or in this case, v, my magnitude. V has to be greater than or equal to the square root of my a component squared plus my b component squared, which means I'm going to have at least 0 every time. If it equals 0, then I must have the 0 vector. And if I have this scalar, and I'm going to talk about what a scalar is in a minute, but if I have this scalar, k, then I can do the absolute value of my scalar k, and then multiply it by my magnitude, or I can multiply it by my vector first, and then find the magnitude of that resulting vector. And if my vector is not equal to the 0 vector, then my vector must be equal to the magnitude times its unit vector. This is the symbol for unit vector. Now I'm going to explain what that is in a moment as well, so just hold on. So when we're talking about our magnitude or our vector, we can break it down into different components. One of the ways that we can talk about our vector is in this way, A, comma, B, where A, comma, B is the location, the tip of my vector. I can write them also in terms of their unit vector. Now the unit vector in the I direction is 1, 0. The unit vector in the j direction is 0, 1. These are the unit vectors, and they call them the principal unit vectors, and that's why we have it the I hat. This is the I hat. So when I see I hat and j hat, this is not complex numbers. This is the components in the I direction, kind of like the x, and the y in kind of like the j, kind of like in the y direction. So using that information, that I can write my vector AB in this manner. So if I have my vector that I started out with, because I like 3, 4, I can write it in this component form. So I can write it as 3i hat plus 4j hat. This is the same thing as 3, 4. When I see that notation, that tells me I must have started right here at the origin, and I went over 3, 1, 2, 3 in this direction, and 4, 1, 2, 3, 4 in this direction, and that is my vector. So I can write it in either way. Now again, we talked about the unit vector. Well, what the unit vector is, it is my vector divided by its magnitude. So if I have my vector, which is 3, 4, then my magnitude of this is going to be the square root. So let me actually do the notation first till I get to it. So my magnitude of v, if this is my vector v, and I'm going to do double because I just feel like it, then this is going to be equal to the square root of 3 squared plus 4 squared, which we know the reason I chose this one is because it's a 3, 4, 5 triangle, is going to give me 5. So my unit vector, so v hat, I see that hat thing, it means I'm in a unit vector. This is going to be equal to my vector, which is 3 and 4 divided by my magnitude, which is 5. Now we haven't really talked about the scalar, but I will in a moment, so I'll give you kind of a heads up. This is the same thing as 1/5, 3, 4, which can be wrote as 3 over 4 plus 5. 3 over 5, I had 4 on my mind, 3 over 5 and 4 over 5. Now this is in the same direction as my original vector. Still in the same direction as that original vector. But if I do the magnitude of this, so v hat, this is going to be equal to 3 over 5 the quantity squared plus 4 over 5 the quantity squared, which gives me the square root of 25 over 25. So I have taken my vector, which had a length of 5, and I've scaled it down by dividing by its magnitude. Same direction, but now it has a length of 1. So that's what we call the unit vector, and you'll see the notation as v hat. Okay, so for some reason it always unlocks my rotation, and I need it to lock rotation. Okay, so now we're going to talk about the scalar multiplication, and we kind of talked about it a moment, so it's like kind of a preview. What a scalar multiplication is it's a number, it's not a vector, and I'm going to multiply my vector by that number, which means each component gets multiplied by that number. So if my unit vector over there, I did 1/5, 3, 5, or 3, 4, my scalar was 1/5. This was 3 over 5, and then 4 over 5. So that is a scalar multiplication. So if you have your original vector and you multiplied it by 2, that was your scalar, then you're going to make the vector twice as long. It doesn't change the direction. If you multiply it by 1/2, it's half as long. It doesn't change the direction. However, if you multiply by a negative number, and this is actually not twice as long, so negative would have been twice as long, but in the opposite direction. So if I multiply by a scalar that is negative, it changes the direction. If I multiply by a scalar that is negative and a different number other than 1, then it also will stretch it or shrink it as well as make it go in the opposite direction. Okay, so now let's look at the properties of the scalar multiplication. So for every vector v, scalars r and k, I can multiply them first and then multiply it by the vector, or I can do it one at a time. If I have the number 1, the scalar of 1, then I get exactly the vector I started out with. I also have something called the additive inverse. So in other words, if I take my vector, I multiply by -1, I get the additive inverse of my original vector, which means when I add my original vector and its additive inverse, I get the 0 vector. I also have the distributive property of the scalar, so I can add my two numbers first and then multiply it to the scalar, or to the vector, or I can do it individually and then add those two vectors together. If I have a scalar and I'm adding them, I can add them first, the two vectors, and then multiply by the scalar. I can distribute the scalar first and then add the two vectors. And then of course, if I have the scalar times the vector v and it is the 0 vector, that only happens if my scalar was 0 or my vector was the 0 vector. Now that we've talked about scalar, what a scalar is not a vector, it's just a multiplier, if you will. So making it 3 times, it's a stretcher, it's a shrinker, it's a reflector. Then I can then talk about the addition and subtraction of my vectors. When I'm adding and subtracting my vectors, I have this vector v and this vector u. I'm adding the components, so a and c, because it's in the I direction, get added together. The b and the d get added together because they're in the j direction. If I'm doing subtraction of these, it's a minus c, because those are the ones in the I direction, and then it's b minus d in the j direction. Now, usually what we do is we consider this the tip to tail. So suppose I start out with my u vector. Here's my u vector. I'm going to do the opposite of my v vector, so it's going to go in this direction, and this is the resulting vector. This is my resulting vector. If I'm doing the addition, I'm going to start out with my u vector. I'm going to add my v vector, my tip to tail. Oh, that should be in red. My v vector, tip to tail, and this is my resulting vector. So let's do a couple of these examples where we're going to do the addition or subtraction of these vectors. And let's be wild and crazy on the second one. Let's throw in a scalar because we can. So the first one is I'm asking to do v plus w. When I do this, I'm going to add my 1 and my 3, and I get 4. I'm going to add my 4 and my -3, and I get 1. So that's the addition. Now v minus w, erase this. And when I do v minus w, it's going to be 3 minus 1, which is 2. And then 4 minus a -3, so that becomes 7. Now I'm going to do this geometrically as well. So I'm going to just write these over here so I don't have to keep scrolling back and forth, because I do want to zoom in. So there's my v, and here's my w. So let's go ahead and zoom in on this thing so I can do the addition and subtraction of this. I'm going to start with my u or my v vector. So I'm going to go 3, 1, 2, 3 in the x direction. I'm going to go 4 in the y, 1, 2, 3, 4. So here is my first vector. Now this is my v vector. I don't know what happened there. This is my v vector. And then from that, I'm going to add to it my w vector. So from this tip, I'm going to go +1, and I'm going to go down 3. 1, 2, 3. So this is my w vector. From my standard position to that tip is my resulting vector. So my resulting vector of v plus w is going to be, you can see I've gone over 4, and I have gone up 1. So that's what I got there. No surprises. Now, let's do the subtraction. I still have my v vector first, so I'm just going to zoom in again. I zoom in. So there's my v vector, and now I'm going to do the subtraction of my w, which means I need to take my w and go in the opposite direction. So instead of going 1. So instead of going right 1, I'm going to go back 1. Instead of going down 3, I'm going to go up 3. 1, 2, 3. This is my minus w vector. And you can see this is my resulting vector. So I have v minus w. My resulting vector then, as you can see, is 2, 7, which is what we got over there. Now, I said we're going to do something wild and crazy. Wild and crazy. Let's do 2 times my v vector. And then, oh, I want to do that. That's always my, I think that's always my blue. So let's do that in blue. Do that in blue, blue, blue. So 2 times 2 minus 2. And then I'm going to add to it my w vector, which is 3 and 1. I'm going to go ahead and add I'm going to do the multiplication first. So I have 4 and negative 4. And I'm going to add to it 3, 1. My result on this is going to be 7, negative 1. That is going to be my addition. Now let's go wild and crazy and say I have v minus 2 w. And so this is going to be 2, negative 2, and then minus 2, 3, and 1. So 2 minus 2, and then I have minus, and this becomes, I'm going to go ahead and multiply this through first, so I get 6 and 2. So I'm going to do the subtraction now, and so this is going to be equal to 2 minus 6, which is negative 4, and negative 2 minus 2 more is also negative 4. So once again, I'm going to come over here and write my vectors v, so that way I don't have to keep scrolling back. V is equal to, and I don't know why it keeps doing that. Obviously, it's something I'm doing. So v is equal to 2, negative 2, and w is equal to 3, 1. Now, my first thing that I did was I did 2 times v plus w. And then the second thing I did was I did v minus 2w. So I just need those there so I don't have to keep scrolling back and forth. All right, let's zoom on in. Zoomy zoom in. So I'm going to take my vector v. I'm going to multiply it by 2. So instead of going right 2, I'm going to go right 4. Instead of going down 2, I'm going to go down 4. So starting with my first vector, I'm going to go right 4, 1, 2, 3, 4, and then I'm going to go down 4, 1, 2, 3, 4. So this represents 2 times v. Now from that, I'm going to add my w. So I'm going to go right 3, 1, 2, 3, and up 2, or up 1. And I should have done that in red. So this is my w vector. And this is my resulting vector. And you can tell from my resulting vector that I have gone positive 6. And I'm still down at negative 3. So let's do my other one. Now my other one is I'm going to do negative 2. So in other words, I'm going to reverse the direction of my w vector. Still have my starting, and this is, oh, I need to also scale this back down. So scaling it back down to there because it's no longer 2. So this is my v. Now I'm going to multiply my 3 times negative 2 and my 1 times negative 2. So that tells me from here, instead of going positive 3, I'm going to go negative 6. So I'm going to go back 6. 1, 2, 3, 4, 5, 6. So that's that part of it. And then I'm going to go down 2. So I'm going to go 1, 2 down. So this represents the vector of negative 2w. And this represents that subtraction, which you can see I've gone negative 4 in that direction and negative 4 in that direction, which is exactly what I got there on both of them. So go ahead and do this one on your own. If you want, we'll discuss it in class. We're going to just keep moving because this is kind of a long video. So I apologize. It's kind of a long video because we're covering a lot for vectors. But we're only just covering just a tip of a very large iceberg. So there's a lot going on with vectors. We're just going to get a teaser in this class. I can decompose my vector in terms of sine and cosine. So this is nothing new. Now, in the regular xy, we have the cosine of my angle is equal to the x over r. R cosine theta is equal to x. Well, guess what? We call it our magnitude instead of r. The other thing we have all day long is the sine of theta is equal to my y value over my r. So r sine theta is equal to y all day long. Well, now we call it our magnitude. And so when we break it apart, we have the magnitude cosine of theta in the I direction, the magnitude of sine in the j direction. So for this, we want to find, for this vector v, we want to find the magnitude, and then we want to find the angle. And then we want to write it in terms of sine and cosine. So the first thing I'm going to do is find my magnitude. This is going to be the square root of 2 squared plus negative 2. So plus negative 2 squared, which is going to be the square root of 8, which is 2 root 2. So there is my magnitude. Now I need to find my angle. So to find my angle, I better know where I'm standing. So I am actually down here. This is my vector down here. It is positive 2, negative 2. And by this point, we should say, it's the tangent. And when I do the tangent theta, the tangent inverse of negative 1, it's going to tell me that this theta is negative pi over 4. But it's also telling me by this point, we should be pretty sick of this. I want the angle between 0 and 2 pi. So I know that I have to add on to it 2 pi. So the actual angle I want is 7 pi over 4. So now to write this in the correct form, and you're going to think, wow, this looks so familiar. This is going to be 2 root 2 as my scalar, the cosine of 7 pi over 4, and then the sine of 7 pi over 4. And you're going to say, but this looks like polar. Well, it does. It most certainly does. I can also write this as 2 root 2, the cosine of 7 pi over 4 in the I hat direction, and then 2 root 2, the cosine, or sine, sine, the sine of 7 pi over 4 in the k hat direction. These are equivalent. This is also equivalent to 2 and 2. Right, find the components of the form of the vector v where my magnitude is 6 and the angle lies in quadrant 2 or 3 with a reference angle of pi over 6, because that's what that's saying. It's my reference angle. So I'm down here. This is my reference angle, which is pi over 6. That tells me the actual angle theta that I want is going to be pi plus pi over 6. Pi over 6 is my reference angle. So this is going to be 7 pi over 6. Now I have everything that I need. I know that the magnitude of my vector multiplied by the cosine of my angle, the sine of my angle, is going to give me my A component and my B component. So I have the magnitude, which is 6, the cosine of 7 pi over 6, comma, the sine of 7 pi over 6 is going to be equal to 6, the cosine of pi over 6, 7 pi over 6, which is square root of 3, negative square root of 3 over 2. And then comma, and then it's going to be 6, and then the sine of 7 pi over 6 is negative 1/2. So my answer is going to be negative 3 root 3, comma, negative 3, which is equivalent to negative 3 root 3 in the I hat direction, and then minus 3 in the j hat direction. So let's take a look at this one. We want to also write this in the correct components. Now we're using degrees. So the first thing I'm going to do is find my magnitude. which is going to be the square root of 3 squared plus negative 4 squared. And you're like, it's a 3, 4, 5 triangle again. And I'm going to say, you are correct. It's 3, 4, 5 triangle. And then my second one, now remember, we need to say where we are. We are down here. So this is 3 comma negative 4, which tells me that when I do the tangent inverse of the negative 4 over 3, it's going to give me the angle that is the negative angle in that quadrant, which means, make sure I'm in degrees, I'm going to add 360 to it. So I have the tangent inverse of negative 4/3. So the angle that they're going to give me is this angle. It's going to be a negative rotation, and I get negative 53.13 degrees. I need it in that interval. So you all know by this point we're going to add 360 degrees to get the correct angle. So I'm going to add 360, and I get the angle, which is 306 point, I'm going to go with 2 decimals, 87 degrees. Okay. Oh, wait. I didn't even have to do all of that. Oh, I did. Then I have to find the unit vector. I was thinking, wow, I didn't need to do that. So I'm going to do this first. So this tells me my vector v is equal to 5, because that's my magnitude. And then it's going to be the cosine of 306, not 60, 306.87 degrees. And then the sine of 306.87 degrees. That's my first part. And then my magnitude, or my unit vector, is 1 divided by my magnitude, which we already know what that is. And then it's going to be 3, negative 4. So this is going to be equal to 3 over 5, comma, negative 4 over 5. So that is my other answer that they're asking for. We're going to do some applications here in a moment. Find the component form of the vector with my magnitude of 3, so that when the vector is plotted in standard position, it lies in quadrant 3 or quadrant 2 and makes an angle of 15 degrees on the negative x-axis. That again is telling me my reference angle. So this is the 15 degrees. The angle I want is this. So it'll be 180 minus that 15 degrees, which is 165 degrees. That's the actual angle that I want, because they're giving me the reference angle. We want to find the components. So my vector is going to be 3, bracket, the cosine of 165, the sine of 165, which is going to be equal to 3, the cosine of 165 in the I hat direction, plus 3, the sine of 165 degrees in the j hat direction. Now I can do the equivalent, so I'm going to take the cosine. I don't know what that happened there. I'm going to take the cosine of 165, and I'm going to multiply it by 3. So this is equivalent to negative 2.8978 in the I hat direction, plus 3 times the sine of 165, and then I get, not the right answer, 3 times the sine, I have to do times the sine of 165, and I do, So this is 0.7765 in the j hat direction. Or equivalently, these are all equivalent. This is equal to negative 2.8978, comma, 0.7765. And there it is in multiple forms in terms of the vector with that angle as a reference angle and that magnitude. Now, we are going to go back to this example. When we did this example, we had to use the law of cosines. Well, now we're going to avoid the law of cosines because we're going to do it by vectors. So my first part of my vector, it says I am 34 degrees off of the north, and I flew 400 miles. So this is the 34, and my magnitude is 400. So my magnitude, now, here's the best part. We can determine however we want to draw where our positive I is and our positive J is. So I'm going to consider this my positive I, and I'm going to consider this my positive J. And you're like, wait a minute, that's different. Well, as long as I'm consistent, it doesn't really matter. So that's how I'm going to orientate my positive I and J. And you're thinking, why am I doing that? Well, because then I can just do the cosine of 34 degrees, the sine of 34 degrees. And that means when I do my turn here, and I'm going to have a bearing of 162 degrees, bam, 162 degrees. I'm going to have some magnitude. I'm going to call this V2 magnitude, and it's going to be the cosine of 162 degrees, and then the sine of 162 degrees. Check that out. Isn't that sweet? And then I'm going to have my last piece, which I come on back this way, and then it's going to have some magnitude, and we're calling it V3 magnitude. And it's going to be the cosine of the 308, because I'm doing everything off of the north, and then it's going to be the sine of 308 degrees. Now, this is what I know by my vector addition and subtraction, is that my components in the J, or in the I direction, which is the first one, the 400, the cosine of 34 degrees, plus my component in the J, in the second component, so that would be the second magnitude, the cosine of 62 degrees, has to equal the magnitude in the third vector and its I component, which is the cosine of 308 degrees. So, because it's an addition of vectors. And then in the J direction, we have to still have the 400, and this will be the sine of 34 degrees, plus my magnitude, my second magnitude, V sub 2 magnitude, the sine of 162 degrees, is equal to the magnitude of V sub 3 and the sine of 162 degrees. Now, for use, to make my life easy, I'm going to call the magnitude of V sub 2 as A, and I'm going to call the magnitude of V sub 3 as B, so it just makes it a little bit easier for me to write this out. Now, this equation then becomes, I'm going to do 400 times the cosine of 30 degrees. And make sure I'm in degrees because I have a tendency to always be in radians. So let me check. Yep, I'm in degrees. So I'm going to do 400 times the cosine of 400 degrees, or excuse me, 34 degrees. 34 degrees. So this is going to be 331.615. And then plus, I'm going to have the cosine of 160 degrees, so cosine of 162 degrees. Don't forget the 162, right? Yep, 162. And that is going to give me, so it's going to be a minus 0.9511. And we're going to call this A, so the magnitude V sub 2 is A, is equal to, and I'm going to do the cosine of 308 degrees, which is going to be 0.615. We'll go with 7B, because remember I did that replacement down here, this replacement and this replacement. So I just didn't have to keep doing writing the magnitude again and again. I get so excited about these. So then I'm going to do, for the second equation, I'm going to do 400 times the sine of 34 degrees, which is 223.677. And I'm going to do the sine of 162. So the sine of 162 is going to be plus 0.3090 in the A multiplied by A. And then I have the, this should be the sine of 308. Let me erase that. That should be the sine of 308. 308. And so I'm going to have the sine of 308, and that's going to give me the negative 0.788 in the B direction. Now, two equations, two unknowns. Keep an eye on the prize. Who am I trying to solve for? I am trying to solve for this last direction. They want to know round to the nearest tenth of a mile the distance in the last leg. So what I'm chasing is my B, okay? So I'm going to eliminate my A to find my B. And I can do it by two equations, two unknowns. I can do it by matrices, because I've learned that in Pre-Calculus 1, or I can do it by substitution, or I can do it by elimination. Now, if I'm doing it by a matrix, then I need to write it in the correct form. So I'd write this as 331.615 is equal to, then I would have 0.9511A plus 0.6157B. And then this would be 223.677 is equal to the point, so this will be a negative 0.3090A minus the 0.77, got so excited here, 0.778 in the B direction. That way, when I pull off the coefficients, I will do that correctly. So I'm going to go ahead and throw that in my calculator with the matrix, and I'll tell you what the answer is. I threw this into my calculator in a matrix form, and it tells me my A value, which I don't need, is 719.87 miles. That's not the part that I need. The part that I want is the B part, which is 573.41 miles. Now here's the thing. My calculator gives me this a negative, and that just tells me that I'm coming back to the origin. So I will take the absolute value of this, because obviously for me, I just want the distance, which is the absolute value. I ignore the negative. So it's 573.41 miles is my answer. And I was able to come to that without doing any weird angle adjustments or anything, as long as I was consistent in terms of what I considered my I and J. Now, I did it so that it was easy for me, and I didn't do anything, laws of cosines, laws of sines, not trying to figure out what this equivalent angle would be off of this. Nope. Strictly made this my I, this my J, and I did it by vectors. Look at that. Vectors and then matrices, which of course are made up of vectors. Boom. There's your answer. Okay, now let's look at Romeo. Romeo, wherefore art thou, Romeo? We're going to be doing the Romeo and Juliet. Nice standard Romeo, Juliet. We have Romeo, we have Juliet. We want to know whether or not the ropes that we have are going to be able to hold this up. Now, what we have is these vectors. So let me just draw the vectors as we have. We're going to call this my first vector. And then with that, I'm going to add to it this vector. And then I have this resulting vector. So up here, and then this is my resulting vector. So basically, I'm doing it with vectors just like I did before. I have this first vector. I'm going to call this V1, my V1 vector. And it's going to have some magnitude. So once again, I'm going to call my magnitude V1 as being A, just because I want to. And then, so this is going to be my magnitude. And then in this direction, I'm going to call this my positive XY. This is going to be 1, 0 times its magnitude. My second vector, V sub 2, so they'll call this V2, my vector V2. This is my V1. Call this my V3. Okay, so my V2, I'm going to call its magnitude B because I can. So my V2 vector is going to be equal to B. And then, so I'm going to do it in components. This is 60. So the angle that I want, because the way I orientated my axes, is going to be 120. So this is going to be the cosine of 120 degrees, and then the sine of 120 degrees. Then I have my third vector. I'm going to call this V sub 3, and it's going to have a magnitude. I'm going to call that C. So C is going to be the magnitude of my third vector. So I'm going to call that C. And then it's going straight down. So it is going to have the 0, 1. Now I know that I'm going to add all of these up. So I'm going to add up all the vectors, and it's going to be the resulting vector is either going to be 3, 1, or 2. Depends on how I look at it. So now let's talk about this, what's happening with this magnitude. So this is one piece that we do know. This magnitude is this Romeo's mass, kilograms, and Juliet's mass in kilograms. However, that is not the magnitude. The magnitude is going to be their combined weight. This is not their combined weight. This is their mass. So to get their weight, what we need to do is take the mass and multiply it by gravity. And this is going to be the magnitude in that direction. That is their weight. Okay, so I have 60 and 65. That gives me 125. I need to multiply it by 9.8 because that is gravity in metric. So I'm going to do 195 times the 9.8. And I get this to be 122.5. So that is my C. That is those two combined, 1,225. All right. Now, I'm going to go right to the chase and say, I'm going to look at when they're both on the rope. So that's the worst case is when they're both on the rope. So we know that vector 1 plus vector 2 must equal vector 3. So I'm going to start in the I direction. When I start in the I direction, it's going to be A multiplied by 1 plus B, the cosine of 120 degrees, must be equal to the 1225 multiplied by 0. Now in the J direction, I'm going to have A multiplied by 0 plus B, the sine of 120 degrees, is equal to 1225 multiplied by 1, because that is in the J direction. So I can get my B with this second equation right here, because this goes to 0. So I'm going to get B is equal to 1225 divided by the sine of 120 degrees. So 1225 divided by the sine of 120 degrees gives me, bam, 1414.5. So this is equivalent to 1.4 kilonewtons. So if my tolerance is 2 kilonewtons, clearly that is going to be in that direction totally fine. So bam. And we also know that one works because their combined weight is 1225, in other words, 1.2 kilonewtons. So the only thing we have to check is to make sure it works out in this direction. So my A is going to be equal to, now this goes to 0, A is going to be equal to negative 14.5 times the cosine of 120 degrees. So I'm going to multiply that by the cosine. The cosine, I lost it. 14.5. Cosine 120. What you're not seeing when I'm groaning over here is the fact that I am hitting stuff on my calculator that is just not good. So A is equal to, this ends up becoming a negative number, so negative makes it positive, 707.25, which is 0.7 kilonewtons. So Romeo and Juliet on that rope are perfectly fine, perfectly safe, and they're not going to crash to their death. Instead, they're going to drink poison. Well, we know how all that ends. Anyways, let's move on to the dot product. So now we're going to look at the dot product. What the dot product is a way that one of the ways that we can multiply vectors. What the dot product is I multiply the I components and I multiply the j components, and then I add that answer together, and the answer is a scalar. One of the results that we get when we do the dot product is that we can find the angle between the two vectors. So the angle between the two vectors is the dot product. Actually, I prefer it this way. I prefer it as u dot v divided by the magnitude of each one of these. I like it wrote better that way. Okay, so I can now do all of my triangle pieces without ever having to do the law of sine and cosine if I know the magnitudes. That's kind of nice. So let's just find the dot product and then find the angle between these two. So I'll do the first two and leave the third one for you. So my dot product, V dot W, and it doesn't tell me the angle, so let's put the theta in degrees. Okay, so my dot product of these two is going to be 3 multiplied by 1. These two get multiplied, plus, and then these two get multiplied. 4 multiplied by -3. So I end up with 3 minus 12, which is -9. The cosine of my angle is going to be equal to the dot product, which is -9, divided by the magnitude of each one of them. So I need to know the magnitude of V. And we know this is 3, 4, 5. We like those. And then I need to know the magnitude of W, which is going to be the square root of 1 plus 3, 9. So 3, 9, 39, 9. So it's a square root of 10. So my theta is going to be the cosine inverse of -9 by the square root of 10. Make sure I'm in degrees. And I'm going to do the cosine inverse of -9 on my calculator divided by 5 times the square root of 10 in my calculator. And I get 124.7 degrees. Nice. So let's do the same thing here. I'm going to do V dotted with, not crossed. We don't learn the cross product in this class. We're going to multiply these two and I get 6. And then I'm going to multiply these two and I get -2. So positive 4. The magnitude of V is going to be the square root of 4 plus 4. So the square root of 8. The magnitude of W is still going to be the square root of 9. So my theta is going to be equal to the cosine inverse of 4 divided by the square root of 8, square root of 9. So I'm going to do that in my calculator. So I'm going to do the cosine inverse of 4 divided by the square root of 8 and the square root of 9. And I get 61 degrees. 61.9 degrees. So almost 62 degrees. So there's lots of applications for this in physics. We'll look at this again in calculus, Calc 3 actually, and of Calc 2 if you're in the semester system, Calc 3 if you're in the quarter system. All right, so I'm going to let you find that angle, and then I just want to say one last thing. If the angle between them, if my dot product is 0, then the two vectors, the angle between them is pi over 2 or 90 degrees, and we say that those vectors are orthogonal. And this is something that we are going to use later if you go into linear algebra in the fall with me, or if you're going to go into Calc 3 with me in about a year's time. We will spend more quality time with a dot product. And boom, there's your vectors.